Good afternoon. My name is Renelle Miles, and welcome to NIH Office of Disease Prevention's Medicine Mind the Gap seminar series. This seminar series explores research design, measurement, intervention, data analysis, and other methods of interest to prevention science. Our goal is to engage the prevention research community in thought-provoking discussions to promote the use of the best available methods in prevention research, and to support the development of better methods. Before we begin, I have some housekeeping items. To participate by Twitter, follow us at NIHPrevents and submit questions using the hashtag NIHMTG. You may also email questions to prevention@mail.nih.gov. There is also a link to the feedback form at the bottom of the videocast page where you can submit questions during the talk. At the conclusion of today's talk, we will open the floor to questions that have been submitted via email and Twitter. Lastly, we would appreciate your feedback about today's seminar. Following today's talk, please visit the ODP website at prevention.nih.gov/mindthegap and click the link to the seminar evaluation under the resources section. Your insights will help us to continue to improve this seminar series. At this time, I'd like to turn things over to Dr. David Murray, Associate Director for Prevention and Director of the Office of Disease Prevention.
Thank you, Renelle. We're very pleased today to have Dr. Phil Bourne with us. He is the Associate Director for Data Science here at the National Institutes of Health. And in this role, he sets a vision for and oversees data science, including the sharing and sustainability of data and tools. Dr. Bourne's own research focuses on biological and educational outcomes derived from computation and scholarly communication through algorithms, text mining, machine learning, meta-analyses, biological databases, and visualization. Before coming to the NIH, Dr. Bourne was at the University of California, San Diego, and in fact, he's not very far from that campus today, since he's coming to us from San Diego. He also co-founded 4 companies, co-founded and was the first editor-in-chief of the open access journal PLOS Computational Biology, and served as president of the International Society for Computational Biology. Dr. Bourne has won several awards and is an elected fellow of the American Association for the Advancement of Science, the International Society for Computational Biology, and the American Medical Informatics Association. At this time, I would like to welcome Dr. Bourne and turn the presentation over to him.
Thank you, David, and good morning, afternoon, evening, everyone, wherever you happen to be. It's a pleasure to give this presentation to you. So I'm going to talk a little about the notion of big data and how hopefully it relates to your particular interest in disease prevention and promoting better health. So the agenda is quite simple, really. We'll look at what's big data anyway, what are the implications for healthcare generally, what are the implications more specifically for NIH, and then let's look at a few examples that are ongoing through some initiatives we're already funding of how this relates to prevention and promoting better health. To end things off. So let's get started with what is big data anyway. I'm frankly not particularly enamored by the term. I like it because it actually brings attention to an important problem. I don't particularly like it because it's not very specific, and it's something that one of the things I worry about, of course, is it being overhyped in the way other things have been in the past. And while I think it's going to have a tremendous impact on biomedical research, I think that's going to come over time. But that when that time is, that time frame is an open question, and I'll get to that in a second. Let me just say that, just to sort of quantify the problem. So we don't know how much data we currently have in the NIH community that we fund. I made a guesstimate at that number by taking what we do know in the intramural program at NIH and knowing that that program is about 15% of all of NIH activities, 85% being in the extramural community. I made a guesstimate that we have 650 petabytes of information. Now, that's quite meaningless unless you refer it to something. So just by way of referral, I found out that in 2012 the Library of Congress had 3 petabytes. So, point being, a lot of information, very complex information in some cases, and of different forms, with some highly structured data, some not so structured. Currently, the NCBI and NLM at NIH have about 20 petabytes of information, which is about 3% of this total. And that could grow as much as 10 petabytes this year, partly because of a large influx of genotyping data from the various institutes and activities. So growing areas growing very fast. I think a very telling number is the so-called dark data. So recently, a group of researchers at NLM actually took a year's worth of PubMed Central full papers, the full text of those papers. They analyzed them and the data that was referenced in those papers and looked at what percentage of that data was actually found in recognized archives, whereas what wasn't. And only 12% was in recognized, sure to be able to retrieve places. 88% so-called dark data, which either sits on a server in a lab or is on a website and atrophies away. So clearly, it's not to say that all of that data is valuable, but much of that data would be required to actually reproduce the experiments in those published papers. And so if 88% of it's being lost, that's a pretty serious situation. The cost that we've estimated, which is actually a reasonably accurate number for archives, data archives that we're maintaining extramurally, this is without NCBI and LM, is a cost of $1.2 billion over the last 7 years. So we're already spending significant amounts of money. With the advent of even more data, that cost is likely to go up. And so we need to come up with new ways of dealing with the situation if we're going to remain cost effective and, in fact, improve our ability to use all this data. So that leads us to the general notion that big data in biomedicine is speaking to something more fundamental than just more data. It's speaking to the need for new methodologies, new skills, new emphasis, new cultures, most difficult of all, and new modes of discovery. And I'll give you some examples of the kinds of things that are happening, which I think are relevant to your community. So what are the implications of this kind of change, and given this data growth at NIH? What are the general implications? And I would potentially argue, and when I discuss this with Francis Collins, he gets nervous when I use the word disruption. I actually report directly to the NIH director, Francis Collins. But I think it's worth thinking about in this context at least. So I want to just illustrate this in general terms from a couple of examples from books that I think are really interesting reading if you're into this sort of thing. The first book, The Second Machine Age, of course, relates to the idea that we had the Industrial Revolution, and now we have a second revolution that's based around data and information. The thesis of this book is that essentially what's happening is happening faster than anyone anticipated. While many people thought we would have Google cars, self-driving cars, the fact that we already have them, and at least in California they tootle around quite a bit, is sort of evidence of something ahead of its time in one sense. And this kind of capability is possible because 750 megabytes of sensor information is being digested every second to drive that car. So it's really having the supporting compute infrastructure that makes it all possible. That relates to Moore's law and other things that I won't get into. The other this point of deception that I like to refer to is, and so we might be deceived at how fast things are happening, relates to this book called Bold. And I'm going to emphasize this with a specific example. So the example I'll use is photography. The first, immediately you'll say, well, what on earth has that got to do with my biomedical research? But just bear with me for a second and we'll get there. So all of this starts off with, on the bottom left-hand corner, with digitization. So as content becomes digitized, even at an exponential rate, things begin to happen. In the case of digital photography, of course, it was the advent of the digital camera, which Kodak invented, but then put on the shelf in favor of their chemical business, which proved to be a huge mistake in this period of relatively low exponential growth curve, where you enter this deceptive phase where people don't fully recognize what's happening on an exponential scale. And I think that's likely what happened to Kodak, and they got back into the market, but way too late when others had really taken that market in terms as the number of digital photographs, and in fact the capabilities of cameras was essentially growing exponentially. This then leads to a disruptive inflection point when the growth becomes enormously apparent, and then that leads to the notion of demonetization, dematerialization, and democratization. And that's clearly what happened in a number of industries, including photography, to the point where Instagram, which is really as an example of an organization that supports communication by images, which is a completely different business model than what photography originally was, has had a huge impact. And Instagram, I think at this moment, is valued more than Kodak ever was. So what's that got to do? Oops, I seem to have, so what does that mean for NIH specifically? Well, you could potentially argue, we don't really know this, that we are at this deceptive point because the digitization of biomedical content, particularly in the form of data, but also in the form of everything, including narrative publications, analysis tools, and so on, and particularly, of course, the advent of electronic health records, is really growing at an exponential rate. And we could be at this deceptive point. Whether we'll actually reach some form of disruption, it's hard to say. But certainly that disruption could lead to what we're actually driving for in any case, which is a patient-centered healthcare system, which I'll say a bit more about in a minute. So that's sort of potentially a large scale what could happen. If that sort of thing starts to happen, there are some pretty serious implications. One of them relates to the sustainability of that data. So on the left-hand side, you can see essentially the NIH budget, and which is flat, or at least in the last year or two, has started to grow slowly, which is good, but certainly not at the rate of what's shown on the right, which is the growth of biological databases that's measured by publications in an annual database issue of nucleic acids research. So clearly, a second grader could tell you probably that this is out of whack. It can't persist. We can't sustain this kind of growth without spending more dollars or becoming more efficient, or some combination of both. And not so long ago, Eric Green, director of the Human Genome Institute, and John Lorsch, the head of GM, director of GM, and I provided perspective on some of the thoughts for how to address this situation, some of which I'll touch on here. Another aspect, of course, is reproducibility. If, as I already mentioned, if 88% of the data for publications is dark data, reproducing those studies is going to be extremely difficult. And this has been identified not just for data reasons, but other reasons as well, in various studies recently looking at these sorts of issues. At the same time, there are acts to sort of change that with the launch of online data journals and a whole series of other very interesting initiatives. And I would say the last implication, which brings us to the notion of the patient-centered healthcare system, is the precision medicine initiative that was announced in January 2015, which has already got a lot of legs and traction within NIH to the point of a number of large awards being made and real activity around that project. I won't get into the details of that, except to say that one of the goals here is to establish a 1 million or more volunteer cohort of participants who are providing a variety of health-related information, from genotyping information through to phenotype information in the form of health records and so on, including other kinds of data associated with lifestyle, biosamples, and so on. So I think this is a great opportunity within this context, and in itself provides some level of disruption, and maybe the end point of that disruption, depending on how you look at it. So what are some of the implications of this kind of set of developments in this future, before I get into some more specifics that perhaps more pertinent to your immediate interests? First of all, I think because of the sheer scale of these activities, open collaborative science becomes an increasingly important, both nationally and internationally. It's ironic to me that we think of data, scientific data, in a global way. We grab data from all over the world and use it, but at the same time, the support of that data is funded nationally, which creates some tension in the system because of it. And increasingly, and I won't go into the details of the number of initiatives we have underway for partnering much more closely with our international and other national funding partners. And so this global, because the reason being, I think it's going to be critical to sustaining this enterprise. I think the implications are if the value of data becomes of increasing value to scholarship. Now, you could dispute that and say, well, the papers are the real value, they always have been. But I think that, of course, I may be drinking my own Kool-Aid, but I think to some extent that is changing. An example from my own career is I have a paper that has over 20,000 citations. No one has ever read that paper. That paper actually describes a biological database which people use all the time. So if people could actually cite the data directly within that database that they use, it would be much better for the people who actually provided that data, and it would give a more realistic picture of really what's going on. But we don't value data citation right now. And again, I don't have time to go into that today, but we're working hard on trying to change that within the NIH. And that's really an example of a cultural shift. I'm going to say a little about improving the efficiency of the research enterprise. And I think that could clearly happen in quite a big way. And that's where we're putting a lot of our energy. And I'll say a bit more about that in a minute. And then training. Clearly, the number of people trained to support biomedical data science and the number of people needed, even now, is totally out of whack. And it's only going to get worse before it gets better, I think. We're putting in the programs that I'm responsible for, which I'll say a little about in a second, we're putting about 20% of our budget into training. And then, of course, there's always this tension and issue about balancing accessibility versus security of particularly, of course, human subjects data, but other data too. And that has to be taken into account. I won't say too much about that today. So what are the implications if we don't act, given this large influx of data, some of which is, may not be particularly usable? And what are the implications of that? So I'm going to give you a little use case that I just heard about last week, actually, when I was essentially a day following Joe Biden at the University of Chicago, looking at the Genomic data commons that's being developed by the National Cancer Institute. So I think the use case relates to a rare disease, but you could also think about this as you get down to personalized healthcare, where you're looking at least very small groups of people with very similar, say, genetic profiles. In some sense, each of which is different to other groups of profiles, that you are getting more precise and you're essentially almost analyzing things like a rare disease. So it's, as you know, complex diseases have all these different traits. So I think it's a different way of looking at it, but ultimately, I think the same tools and thought processes are very useful. So let's look at a specific example. So diffuse intrinsic pontine gliomas, DIPGs, is a form of brain cancer that occurs in about 1 in 100,000 individuals. It peaks at around 6 to 8 years of age, and as you can see from the survival curve in the bottom right, is not very encouraging. It's in the order of 9 to 12 months. And surgery for this kind of condition is not really possible. Chemotherapy is ineffective, and radiotherapy is typically only transitive and adds very little time to life expectancy. So clearly a distressing and important problem. So that was the message there. There have been a number of genomic studies, and I think one that really kicked this off, I'm going to use this to illustrate the point I want to make, was essentially the identification of histone mutations, as recurrent driver mutations, and this was discovered in about 2012. Unfortunately, that information in terms of therapy couldn't really be used. There was no way of treating it relative to those particular mutations. However, what happened 3 years later in an expanded data set that was actually accessible to 2 other groups as well. Those groups and then the original group themselves identified mutations in ACVR1 genes as a secondary co-occurring mutation. Now, this proved to be extremely important because that's a targetable. It's targetable by a tyrosine. It's a targetable tyrosine kinase for which there are inhibitors already under development. So this discovery actually provided some possibility to begin to treat this condition. Now, so what that means is there's about 300 of these such patients a year. 60 are predicted to have this mutation. And so if this large-scale data set was available and it was integrated more with TCGA and so on, TCGA being Cancer Genome Atlas, it would have been identified potentially much earlier. That's the point. If that data had been shared and accessible to many different researchers, it potentially, I say potentially because it's still very early days of how effective the drugs are going to be, or the drug's going to be, but potentially there could have been life savings going on here because of it. So I think it's really important that we conform, and the way we share data, we share it openly, and as accessible as many researchers in a usable form as possible. We call this the notion of this ability FAIR, which is the notion of find, that the data be findable, accessible, which means usable, interoperable, and reusable. And there's been a lot of work by the community around the so-called FAIR principles, and that's highlighted in that paper on the bottom of the screen. So the Commons offers is a means to be fair. And what I mean by that is think of a commons as, first of all, of the internet and how the internet was formed. Essentially, the internet didn't start off as one great conglomerate network. It started off as a series of small networks, which at certain time points saw the merits in merging together and becoming interoperable. And so it ultimately grew into one large internet. I would argue that we're now looking at this idea of the internet of data, where we have these discrete pockets of data as there were networks. And the motivation and the value of seeing that merge in some way or being jointly accessible is compelling and will drive the so-called internet of data. We're trying to ourselves at the NIH drive this through the development of what we call the commons, which effectively is, while it's physically discrete, as networks are, it appears to be a single entity where data, analytics, narrative, and other components, including final publications, can be shared in a cooperative environment. And so there are examples of, if you think of these subnetworks that already exist, which are essentially their own little commons. So there's the Human Microbiome Project, which is about 40 terabytes of data that sits, and most of this sits on cloud resources, so this happens to sit on Amazon Cloud Resources. And then there's the NCI Genomic Data Commons, which is about 5 petabytes. So that's an effort to bring together a lot of genomic data from various sources under the NCI umbrella. And it's so compelling, I think, from that, at least for me, from that example I told you, that while this has only just been launched and it's currently 5 petabytes of information, it's likely, I think, to see very extensive use. And we're already seeing that with HMP. It was so compelling that, in fact, the person who runs it, Bob Grossman, is the person on the left in that picture, was being encouraged by Vice President Biden, who visited last week, to get on with the job. So as part of the Cancer Moonshot. So I think there's a lot of compelling reasons for exploring these types of environments. Now, and so to that end, we're spending within the program that I run, it's called BD2K, the Big Data to Knowledge Program. We're spending a very significant part of our budget now, and more in FY17, on the idea of developing the commons concept. So what that means is really indexing resources that are in this environment so they can be found, developing standards that the community can learn about and adopt, or collecting standards so they've already developed to standardize data as much as we can. It provides cloud and high-performance computing facilities, and it also at least has the promise of a certain level of sustainability, which I won't say too much about today, but because I want to get on to use cases that I think are relevant to you. But this is clearly important. At the same time, we also spend a very significant amount of budget, which is about the order of $60 million, on data science research efforts. And it's those that I'm going to really focus on for the rest of the talk, with hopefully some use cases that are developing around data science research that have relevance to your own particular interests and in prevention and so forth. So that's what I'll focus on for the remainder. So let me give you some of these examples that are being applied to disease prevention and promoting better health. The first one is actually not from us, but I just use it as a point of reference to highlight some differences between this and what we're doing. So this is actually an example from a number of labs, but from Søren Brunak in particular, who's a colleague of mine in Denmark. And this is a comorbidity network that's been developed over the last using 15 years of electronic health records for the whole Danish population. And I think it's just a telling, and to me at least, who's not actually in this business, but predictive tool, just constructed in a very simple way. So essentially all that's gone on here is through ICD-9 codes and so on, disease conditions have been identified which represent the nodes in this network. The edges in the network and the thickness of those edges represent, but just based on what actually happens to the Danish population, which, relatively speaking, is quite homogeneous, from those records. So it's an expression of the likelihood of going from one condition to another. So, for example, if you have COPD, there's over time there's a strong likelihood that you'll have respiratory failure. Now, of course, at that level, none of this is particularly surprising. But as you start to drill down into these networks, you find some interesting connections. And it seems to me, at least, that they offer significant potential for intervention. I think, and this will be good to have in the discussion, because I want to learn about this, is what the part that I worry about is the translation. In other words, how do you get simple tools that, in some senses, this represents, in the hands of care providers and having them use them effectively to offer intervention. So that was just an example. That there's no, it's just looking exactly what's in the record. The question is, can you learn from what is in the record? And that is the objective of one of the BD2K centers that we're funding. It's called the Center for Predictive Computational Phenotyping, which is led by Mark Craven at the University of Wisconsin. There's a series of projects, different types of phenotyping, which you can see there on the left, ranging from neuroimaging, EHR, and I'm going to focus on the EHR piece here, and obviously, all the way down. And so those are different phenotyping efforts. And then there are labs that take that data and are doing certain things with it. Some is not, I would say, mundane, but on the other hand, it's incredibly important data management, assessing the value of the information, statistically and otherwise, and creating representations that cross-cut data types, and then the stochastic modeling aspect of it. So all of which is really important. So let's just look at the EHR-based phenotyping. So essentially what's happened in the past is the idea of retrospective phenotyping, which is really what I just showed you on the other slide. But then the question is, can you do prospective phenotyping? Can you predict not just by what's actually happened, but really what's based on what's happening and happened? But can you learn more than what's immediately obvious in the data? I mean, in other words, can you use existing EHR data as a training set and use machine learning algorithms to actually do some real prospective phenotyping and make predictions about the likelihoods of new conditions emerging? And that's exactly what this group has been playing around with. This is indeed very formative research. But I think I'm showing it to you because I think the idea is to illustrate when you have large amounts of data, and this is based on 1.5 million subjects from the Marshfield Clinic across all ICD-9 codes, then what you can see in this kind of presentation is the area under the curve. So the farther to the right, the more predictive power there is. And so after 1 month and 6 months, you can see certain variabilities of predictive power to predict phenotypic outcomes based on this large this large cohort of patients. As I emphasized, very preliminary but promising as useful tools going forward based on using patient-centered outcomes from large cohorts of information. Let's look at a different example, which comes from the Mobilized Center, different type of data, again, with the ability to predict or provide the ability to potentially make interventions. Again, this is still very formative research. This is from Scott Gelb's group at Stanford. So this is just one of their activities, but they're essentially using ASMEO smartphone data, which provides mobility data and BMI data. And it's based on 2 million subjects worldwide. I think that's an interesting aspect to it. This is a global study representing 74 million days of activity. So each activity is a data point in this, and therefore there's over 100 billion data points, which is much larger than the NHANES study on mobility that was done and other aspects that were done by the CDC. So this is essentially a giveaway of data that's coming off this app and being streamed to ASMEO, in which the DELF group has access to. So first of all, on the top right-hand side, you can see that there's about 40,000 individuals age 60 or plus, so you can see the age distribution. So it's not just that old fuddy-duddies like myself don't use cell phones and smartphones. The indication would be we do, and that we got a reasonable age distribution. Well, they had a reasonable age distribution to do this study. Looking at the counts of BMIs from this, you can see that follows a pretty normal distribution. Close to 30% of the population regarded as obese worldwide. Sad but true. Then when you start analyzing the activities of folks using this data, first, one of the things that's, I think, interesting but not a new finding is that first of all, for those of you who use these devices, you tend to set yourself for 10,000 steps per day, and myself included, often or more than often, don't actually reach those 10,000 steps. And so, interestingly here, based on gender, men typically cover significantly more steps than women, and the sort of and how it relates to BMI category sort of follows parallel pathways. And it's obviously activity tends to decrease with increasing BMI or the other way around. So there's nothing particularly surprising in this, except it's confirmation of a study about motion that was done, just in one example of studies that was done about the gender difference a number of years ago. So, but then when it gets more interesting, which is shown on the right, is the notion of bout duration. So it turns out, at least according to this very preliminary data, large-scale data, is that even with one bout of greater than 5 minutes of significant activity per day, BMI tends to be lower. And then it sort of actually flattens off, and then and certainly after a number of bouts, it actually begins to go up. So I think the relevance of that data is still yet to be fully understood, but I think that this is just coming off raw reads from these devices. So I think it certainly offers a rich field of study to begin looking at this, to understand how you can offer interventions from large-scale experiments like this. Looking at it on a planetary scale, there's they've used the Gini coefficient here, which is usually used to measure economic inequality in a given country. Here it's used to measure obesity inequality. So essentially what that means is the activity inequality, the larger the number, the more variance there is in the population with respect to the level of activity. At the same time, on the other axis, we have obesity. So there's interesting outliers like Vietnam. That could be just that there's not enough data, or it could be that there's something significant going on there. But beyond that, again, the kind of things that you could perhaps imagine in terms of the variance in a given community. So in the United States, for example, there's a large activity inequality and overall high levels of obesity. So it's, that's quite clear, and you can then break that down onto a more geographic level. So on the right-hand side, just based on this data, it's now just in the United States. It's data that's actually on the y-axis is the average level of obesity in a given city within the U.S. And again, perhaps not surprisingly, but certainly worthy of consideration, is it's sort of along the lines, city by city, of what you would expect. Interestingly, on the x-axis is data that's taken directly from Yelp, which is public and downloadable. And essentially what it's doing is it's measuring the number of fast food restaurants within certain regions, within regions of these cities. And the more fast food restaurants there are, there tends to be higher levels of obesity. again, not perhaps surprising, but certainly a correlation there. Then the question becomes, what do you do with intervention? Be really interesting to start intervening based on this kind of data. And in fact, some of that is going on around work around smart cities and so on, and healthy cities, to try and tip this balance. It'd be very interesting in times ahead to look at the impact that this kind of data tells you about what happens when you make interventions, either the kind of food restaurants you have or the kinds of layouts of cities to encourage more activity and so on. So I think that's all very promising. Then give me one more example, which brings in yet another type of data from different types of sensors. And we've seen one kind of sensor that was used in the smartphone to get mobility, but of course there are clearly others. And the mobile sensor data to knowledge center, which is I'm blanking. It'll come to me in a second. They're not only using existing sensors, but they're also developing sensors themselves, for example, in smart glasses to look at pupil dilation and so on, and chest monitors and so on. Again, a lot of these kinds of developments are very formative. An example of measuring of one chest band is essentially using a cell phone to get a constant readout, a constant EKG readout. The problem with that right now is just trivial things. It just drains the battery in no time at all. So these are sort of examples of early stage kinds of developments which I think will become important over time. And then associated with those types of sensors, you're looking at different kinds of exposures, whether it be exposures to different types of foods, to tobacco products, alcohol, and so on. And then what are the behaviors, using these sensors to measure behaviors relative to these kinds of devices. I'm going to give you, and then essentially that leads to outcomes which can be measured and potentially interventions ultimately made. Again, this is all very formative stuff, but I think nevertheless has promise. So just looking at one example, so this particular group is working on two major areas. One is chronic heart failure, and the other is smoking habits and cessation. So they have developed sensors to determine whether when someone actually lapses in smoking cessation. So that turns out to be an interesting and intriguing problem in itself, because first of all, the lapse is usually fairly ephemeral, and there's numerous confounders in that. And just to give you an example, on the right-hand side there, you can see exactly how different people hold cigarettes, and so all of that leads to different types of motion, which needs to be distinguished from other kinds of motion like yawning, moving your hand to your face, eating, and so on. So I think that they've actually made some progress on that in controlled experiments, so that they can, with the devices they're using, detect times and duration of first lapses. And that then leads to some observations, so that the first lapse usually is very short duration, in which they get longer afterwards. And also that how patients report lapses doesn't actually reflect very well what they actually detect from the sensors. So again, this is sort of very early stage work that points to the possibility of some form of intervention. So in summary, I think from my point of view, big data offers unprecedented opportunities for what can happen going forward, but they require a cultural shift, which is relatively small for some communities and large for others. And for example, in the genomics community, there's really a culture of sharing and shared resources and so on already. In more clinical areas, not so much. Either way, even further cultural shifts are never easy. And incentives are clearly critical. I don't really say anything very much about that, but that there's different areas we're working on. I could certainly try and answer questions about that. I mentioned the commons environment and these efforts, both by NCI, by Big Data to Knowledge, and a number of others. NIEHS is now developing a commons. Human Genome is in the process of developing a commons, all under the FAIR principles, where we hope to foster a much more interchange and sharing of information. And so I'd certainly like to hear from you. So we're trying to encourage change, and I'd very much like to hear opportunities from you as to how this kind of data could be used effectively. When I talk about this to Francis Collins, he said, well, this is all great, but give me the use cases. Show me how, over time, this is going to have a real impact on healthcare. And that's what I need your help with. So thanks very much. I would just say that it's a team effort by no short measure. And my role is across the NIH, the trans NIH role. I have a small team of great people who work on this. But importantly, at the bottom there, or equally importantly as the great team, are the representatives from across the 27 institutes and centers of NIH who form the executive committee and help move these initiatives forward. So thank you for that, and I'll leave a web page and an email address if you wish to contact me about this later. And hopefully I've left some time for questions, and hopefully I've been talking and that there's someone still out there. So thanks very much.
Thank you, Dr. Bourne. Yes, we're still here.
That's a relief.
And we do have questions.
So I'll start with one. It's kind of a two-part question. First, the statement is, doesn't the scientist change in a world with massive amounts of data? And they say...
Sorry, I missed that. Doesn't the scientist what?
Doesn't the quote-unquote scientist change in a world with massive amounts of data? And they follow that by saying, it seems the difference between Instagram and the use of electronic health records data is that anyone can use the former, whereas very few scientists currently have the expertise to use the available data, though many may have questions they want to answer. The gap between training and demand seems like the rate-limiting step.
Well, I think those are good questions, comments mainly, in which I could also comment on as well. I mean, I think that scientists, that there is a need to change, and I don't think there's any question across the biomedical sciences that there's a growing need, a growing necessity to have training in analytical techniques that may not have been necessary in previous generations. We've seen this happen. I mean, I'm basically a bioinformaticist originally. So we saw this happen 20 years ago when we were pushed into it with the Human Genome Project. And so that did lead to a new, and I have a whole lecture about this, but I won't bore you with that now, but how that group of people, bioinformaticists, sort of evolved over time and how they became integrated into the system and ultimately became equal partners in the enterprise. So that led to that was the result of change. This is change as well. In terms of the usability of data, I think that by different groups, it's true that anyone could use, well, anyone except my wife. I didn't mean to say that. Could use Instagram, but you can't necessarily make sense of electronic health records. But I think part of that has to do with how we present, visualize, and create user interfaces to enable meaningful use of this kind of information. There's lots of caveats there. For example, if you have an app which suggests some form of intervention, and you make that intervention and whatever it is doesn't improve, can you sue the maker of the app? And there's all of these kinds of issues which have to, I think, at a very formative stage, we're still working through. But and I think there's no question that it really behoves the people who are already working in this field to address the usability question. And then, of course, there's the meaningfulness of the interpretation that people make of data. So none of these are easy problems, but there's, I think by training as many people as we can, we'll at least make some progress.
And there's a follow-up. Can NIH ICs develop commons-based initiatives? Can the commons be used to integrate electronic health record in NIH-supported research across the U.S. now?
So we have these initiatives going on, and I mentioned these various commons, and we call them pilots actually, that are going on. I mean, it's very early in their development, so I didn't go into a lot of the details of the evaluation of the success of those. I would say that the goal is, my personal goal is in 5 years, I'd like to be able to say, well, looking at what we're doing now and how we're managing data and how much it's costing and how much usage there is and so on, that we've really increased our efficiency, and by, let's say, I'm shooting for, say, 5%. Well, 5% of $32 billion a year is not insignificant. That would be a lot of new R01s doing research. So, that's, it's a lofty goal, but that's the kind of way we're thinking about it. But how do you get there? And so the issue is that the program I described, BD2K, is putting the order of, I don't know, this year probably $40 million into fostering this kind of activity. But that really, frankly, is a drop in the bucket of what's actually needed. And I've been having these discussions with Francis Collins and Larry Tabak. We've now formed a task force to determine how we can, what's the right things to do and how to accelerate the process so that, we get to better endpoints without completely draining the bank. Just to give you an example which got their attention, is I showed you data, or not data, but I showed you a bullet that I didn't show you the data behind it, that we spent $1.2 billion in the last 7 years on data resources. Well, if you also recall, I said we're saving 12% of the data currently from publications. So if you saved it all, we'd be spending $1.2 billion a year just on that data. So clearly the costs are going to continually increase as the data increases. We need to figure out ways of bringing those down. So the commons is a way of getting there. But to answer the question, how do the ICs get onto the on-ramp? And that's one of the issues that I've asked this task force, or asked Francis, who's chairing it, to have the task force address, because this is a critical issue. It's we have a very small office, and as you saw, and the people in the ICs, the EC group, they give a piece of their time to help move this forward, but they're only working a small percentage of their time. So we need lots of engagement across the ICs, and clearly other organizations like the National Library of Medicine, NCBI, the Center for Information Technology, all have roles to play here, and that's all being considered by the task force to how to move this forward.
All right, thank you. We have another 3 more questions. Hopefully we have time to get to at least some of them. For those on the phone and watching, if you have questions that we don't get to, please email us at prevention@mail.nih.gov, or you can email Dr. Bourne, philip.bourne@nih.gov. So, Dr. Bourne, could you comment on the role, helpful or obstructive, of large-scale companies collecting data to commercialize it?
Yes, interesting question. So, I mean, clearly that is going on in droves in lots of industries. The question of that data within the healthcare industry, particularly as it relates to electronic health records, is, I think there's, it's not. I mean, certainly there are projects within BD2K who have access to that data. And in fact, some of these companies are actively developing patient-centered outcomes of their own using this data, but others are not, or don't seem to be, at least anyway, from my observation, in quite the same way, and are willing to, at least provide that information to researchers for purposes of sort of leading to better outcomes. But it's not probably where it should be, and I think the ability to operate certainly is not as easy necessarily for researchers as it is in other countries which have, for example, more socialized healthcare systems. On the other hand, the group at Harvard, who's one of the centers through Zach Kahane of BD2K, has access to, I think, 55 million Aetna records, for example, looking at prescriptions and other aspects of those records. So I think it's spotty in how that data is accessible. Of course, I'm not touching on the whole consenting issues and the whole privacy issues, but clearly those are a big part of it. But just in general terms, I think we've got quite a long way to go. But I think initiatives like the Moonshot of precision medicine particularly for the consenting aspect and the accessibility of information, I think will help drive change. But it's going to be very important as those projects go forward that the value to the participant can be seen at a relatively early stage to keep them engaged in the increasing provision of information. And then, of course, having healthcare providers also participating is going to be critical.
Okay.
Thank you. We're reaching the end of our time, and though we have lots more questions, we promised that we would wrap at 2:30, so I think that we're going to stop at this point. Would encourage participants who didn't get to pose their questions or who have follow-up questions to send an email to us at the Office of Disease Prevention or contact Dr. Bourne here at NIH. Dr. Bourne, thank you very much for your time today. We appreciated your presentation and the discussion that we just had. Thank you.
Thank you very much.
And for those of you on the phone, thank you for participating. On the Mind the Gap website, which is again prevention.nih.gov/mindthegap, you will find several resources for this talk, including the slides, references, and a link to complete an evaluation. Your feedback is very important to us as we plan future sessions. Thank you again for your time.